My name is Ryan Goethals, and I'm the co-founder and CEO of MicroLED, where our mission is to eliminate the need for diesel. And we're going to do this using novel solid-state metal air battery technology. So right now, the world's heavy industries rely on diesel primarily for portable power, all the way up to large transportation like rail and maritime. These emissions contribute greatly to global warming on the scale of about 10% of emissions each year. On top of the planetary impact, there's also a human health angle that is overlooked. So what we've focused on is that particulate matter, or PM2.5, is also emitted with burning of diesel, and this has been linked to lung disease and other health complications, greatly impacting the world's population. So if we can reduce or eliminate the need for diesel, we can both help the planet, but also people living on it. Current energy storage technologies like lithium-ion have a fundamental flaw. They're limited by their capacity. When you've discharged your battery fully, it needs to go down for charging, which is very different than if you use up all the fuel in a fuel tank and you can simply refuel the generator. So that downtime, as well as the expensive infrastructure and maintenance of that infrastructure, are huge hurdles for existing battery applications. And finally, the safety risk is monumental as you start to aggregate more and more energy for these large systems. So specifically, propagating battery fire is a huge risk for maritime or for rail. So at MicroLED, we acknowledge this challenge, and we're trying to solve it using our novel solid-state metal air battery tech. And the main focus here is that we can create a metal fuel of sorts, is how we refer to it, using a swappable anode method. And I'll get into that in a minute. But just to focus in on how we can compete or beat diesel, it really comes down to cost. So the end goal here is to also be cost competitive with these fossil fuels while improving safety through the use of an aqueous or water-based battery, so reducing the risk of fire substantially. So how we're approaching this problem is we've actually separated the discharge and the charge of a traditional battery, and that is thanks to our separable system. So right now we use zinc sheet metal as our fuel. This is a standard anode material. We input that into our metal air generator. So you can imagine this as the primary discharge of your zinc air battery, where we combine oxygen in the air with that zinc metal to produce electricity through an electrochemical reaction. So this looks and behaves very similarly to a standard zinc air battery. And the best part is that there's no emissions at this stage. So the customer has no emissions on their site, and the only byproduct is that oxidized zinc or that oxidized metal. What's great about zinc and zinc oxide is that this is a reversible reaction. So we can take that zinc oxide byproduct, use renewable electricity to remove the oxygen from the zinc and redistribute the zinc metal as fuel again. So when you have this closed loop fuel system, you end up with substantial environmental benefits, about 90% reduction in life cycle emissions, on top of that full removal of scope 1 emissions for the customer. And as I mentioned, we do have a cost benefit as well, where we can price match or price beat diesel in most markets. So the actual battery itself is, as I mentioned, very similar to a zinc air battery. What we've done differently, though, is we've swapped out the traditional liquid electrolyte for a solid-state hydrogel electrolyte. This allows us to package the air cathode and that hydrogel electrolyte into one side of the cell, and then the anode serves as the other side. So you can fully separate those two pieces. We have no reaction, no current, but when you bring them together, it acts just like a traditional metal air battery, providing electricity to your circuit. So this architecture was designed and patent pending through the University of Pennsylvania, where the original team met. And just to give a demonstration of a small cell on the right-hand side here, this is what the assembled cell looks like. So you have current collectors on the top and bottom, and then your stack of battery material in between. Notably, this is an open system, so there's no wrapping or no casing. It's all open. And we're able to do roughly 1.2 volt nominal discharge, similar to traditional zinc air batteries, with roughly 1.5 amp hours in this form factor. The actual chemical pathway here, very quickly, is oxygen comes in through the air cathode with a catalyst to promote that reduction of oxygen into the cell, forms hydroxide in the hydrogel salt. That hydroxide transfers across the electrolyte. The oxygen bonds with the zinc through a two-step process, resulting in zinc oxide as well as your electricity. And then the hydrogen goes back into the liquid solution. So how this works in practice